This is part 209. It's all data, okay? So line 18s, Redshift, light, inertial navigation system, angular velocity, Wow Seti. So it's basically whatever these words mean. I looked up the meanings of them on Wikipedia, okay? So this is the alien radio signal there. So I'm going to Google Galaxy Redshift survey, quotes from Wiki, survey results. The principal results obtained for the field of cosmology by the 2DF survey are: the measurement of the density parameter of non-relativistic matter, baryonic matter, plus dark matter, plus massive neutrinos, detection of baryon acoustic oscillations, and as a consequence, the relationship between the density of baryonic matter and dark matter. Limits on the contribution of massive neutrinos to dark matter, putting a limit on the sum of the masses of the three families of neutrinos at 1 point eV. All these results are in agreement with the measurements of other experiments, notably those of WMAP, that confirm the standard cosmological model. And there's a graph there. I don't know if you can see that. It's a shape. I can't even read it. Something Great Wall. Sorry, it's hard to detect it. DTFE, reconstruction of the inner parts of the 2DF Galaxy Redshift survey. The 2DF survey also yields a unique view on our local cosmic environment. In the figure, 3D reconstruction of the inner parts of the survey is shown, revealing an impressive view on the cosmic structures in the nearby universe. Several superclusters stand out, such as the Sloan Great Wall, which is this one here, the largest structure in the universe known to date. Theory: the shift in interference fringes can be viewed simply as a consequence of different distances light travels due to the rotation of the observer. The simplest derivation is for a circular ring rotating at an angular velocity of w rot, I guess. But the result is general for loop geometries with other shapes. If a light source emits in both directions from one point on the rotating ring, light traveling with the rotation direction will travel more than one circumference around the ring and hit the light source from behind after a time t1. So there's the graph there. Light traveling opposite directions go different distances before reaching the moving source again. And there's the mathematical equation there. So it talks about the distance the mirror has moved in that same time, eliminating from the two equations we get. Likewise, the light traveling against the rotation will travel less than one. So I'm wondering, if it's talking about light and it's talking about mirrors, I wonder if this is supposed to be for the space elevator. I'm not sure, but it sure looks like it. Maybe this is one of the things you can use for the obsidian mirrors. So anyways, you can look that up on Wikipedia to take a look at it a little closer. It says, we imagine a screen for viewing fringes placed at the light source, or we use a beam splitter to send light from the source point to the screen. If the light were pulses shorter than AT, there would be no interference, but applications use steady light, and shifting interference fringes are seen due to the presence of the two beams of light on the screen that left the source at different times and hence have different phases at the screen. This causes fringes to shift in proportion to A and W rot. In the case of light propagating in vacuum, pre-relativistic theories and relativistic physics predict the same. In other words, in the case of propagation in vacuum, a SAGNet experiment. There we go. Remember the SAGNet effect came up in with the space elevator, so I guess this can be used for the space elevator. I'm gonna have to add that word into either the tags or something, because obviously this has something to do with it. A SAGNet experiment does not distinguish between pre-relativistic physics and relativistic physics. Both predict the same. And this is for the mirror and light. Okay, so when the SAGNet setup has the light propagating in fiber optics, then the setup is effectively a combination of a SAGNet experiment and the physio experiment. In glass, the speed of light is slower than in vacuum, and the fiber optics itself is a moving medium. In that case, the relativistic velocity addition rule applies. Pre-relativistic theories of light propagation cannot account for the physio effect. By 1900, Lorentz could account for the physio effect, but by the time his theory had evolved to a form where, in effect, it was mathematically equivalent to special relativity, Hence, only relativistic physics can account for the physics of fiber optic segment interferometers. A clock attached to the ring would run slower due to its velocity than inertial observers. The light frequency of the moving source would increase to cancel that. Also, Doppler effect cancels out, so the Sagnac effect does not involve Doppler effect. In the case of ring laser interferometry, it is important to be aware of this. When the ring laser setup is rotating, the counter-propagating beams undergo frequency shifts in opposite directions. This frequency shift is not related to Doppler shift. So one of the things is getting the thing to rotate around what you're doing to get a constant beam to shift it up. So the Sagnac effect is not an artifact of the choice of reference frame. It is independent of the choice of reference frame, as it is shown by a calculation in Book's symmetric tensor for an observer at the axis of rotation of the ring interferometer and rotating with it yielding the same outcome. Now, talking about rotating, we're also trying to build an outer shell that rotates as well on a spaceship. So it could be for that, or it could be for the other thing. I'm not sure what it's for. If one starts with the Minkowski metric and does the coordinate conversions, x equals that, and that equals that, foreign coordinate, the line element, the resultant metric is this, where t is the proper time for the central observer, r is the distance from the center, 0 is the angular distance along the ring from the direction the central observer is facing, z is the directional perpendicular to the plane of the ring, and w is the rate of rotation of the ring and the observer. Under this metric, the speed of light tangent to the ring is c plus rw, plus minus rw. Depending on whether the light is moving against or with the rotation of the ring. Okay, there you go. What speed of light. So in turn, inertial navigation system. So I googled that to find out what it means. So gyroscopes measure the angular velocity of the system in the inertial reference frame. By using the original orientation of the system in the inertial reference frame as the initial condition and integrating the angular velocity, the system's current orientation is known at all times t. Accelerometers measure the linear acceleration of the system in the inertial reference frame, but in directions that can only be measured relative to the moving system. Since the accelerometers are fixed to the system and rotate with the system, but are not aware of their own orientation. However, by tracking both the current angular velocity of the system and the current linear acceleration of the system measured relative to the moving system, it is possible to determine the linear acceleration of the system in the inertial reference frame, performing integration on the inertial accelerations using the original velocity as the initial conditions. Using the correct kinematic equations, remember kinetic energy keeps coming up, yields the inertial velocities of the system, and integration again using the original position as the initial condition yields the inertial position. Error. All inertial navigation systems suffer from integration drift. Small errors in the measurement of acceleration and angular velocity are integrated into progressively larger errors in velocity, which are compounded into still greater errors in position. Since the new position is calculated from the previous calculated position, and the measured acceleration and angular velocity, these errors are cumulative and increase at a rate roughly proportional to the time since the initial position was input. Therefore, the position must be periodically corrected by input from some other type of navigation system. The inaccuracy of a good quality navigational system is normally less than 0.6 nautical miles per hour in position, and on the order of tenths of a degree per hour in orientation. If navigation systems malfunction, they can send planes off course. Accordingly, inertial navigation is usually used to supplement other navigation systems, providing a higher degree of accuracy than is possible with the use of any single system. For example, if it is terrestrial use, the inertially tracked velocity is intermittently updated to 0. By stopping, the position will remain precise for a much longer time, a so-called zero velocity update. Control theory in general and Kalman filtering in particular provide a theoretical framework for combining information from various sensors. One of the most common alternative sensors is a satellite navigation radio, such as GPS. by properly combining the information from an INS and the GPS system. The errors in position and velocity are stable. Furthermore, INS can be used as a short-term fallback while GPS signals are unavailable, for example, when a vehicle passes through a tunnel. So this PDF file comes up from a time-delayed integration drift scanning, www.astro.yale.edu. So it's time-delayed integration drift scanning. George Jones, June 7th, 2006. George, if suitably modified, Russ's approach will work. Okay, so these are people talking in a forum, and I grabbed their notes because it was interesting what they had to say, okay? George, if suitably modified, Russ's approach will work. Given accelerations and initial velocity, you can generate a column of velocities. Okay? Yes, I wasn't mathematically explicit, but this is what I meant by. Also, a sum of rectangles has to be taken, and the t is the time interval between readings, not the time of the readings. Your iterated formula treats the acceleration as constant over each time interval, and thus finds velocity as an area under the acceleration time graph by summing a bunch of rectangles each having acceleration as height and a time interval as width. If the time intervals are all equal, you can simply repeat this procedure to generate displacements. Yes, this will work, but it would be more accurate to do as much as possible analytically first. For example, consider the rectangle rule in one time interval. So A is constant over the time interval, i.e. something like the following. I haven't been particularly careful, so I might have screwed it up a bit. So there's his calculations. And then integrate again, he's using those calculations. Of course, this just results in the standard constant acceleration formulae. A third integration is necessary to calculate the mean, but if equal time intervals are used, I guess a good approximation would be just to take as mean a finite sum. So Wolfpack Diver, March 10, he wrote, double integration of raw acceleration data is pretty poor estimate for displacement. The reason is that each integration you are compounding the noise in the data. If you're dead set on working in the time domain, the best results come from the following steps. Remove the mean from your sample, now have zero mean sample. Integrate once to get velocity using same sum rule, trapezoidal. Remove the mean from the velocity. Integrate again to get displacement. Remove the mean. Note if you plot this, you will see drift over time. To eliminate sum to most of the drift trend, use least squares fit. High degree depending on data to determine polynomial coefficients. Remove the least squares polynomial function from your data. A much better way to get displacement from acceleration data is to work in the frequency domain. To do this, follow these steps. Remove the mean from the acceleration data. Take the Fourier transformation, FFT, of the Excel data. Convert the transformed Excel data to displacement data by dividing each element by minus omega to the power 2, where omega is the frequency band. Now take the inverse FFT to get back to the time domain and scale your result. This will give you a much better estimate of displacement. Hope this helps. One more thing, if anyone is wondering where the omega 2 is coming from, try taking the analytical second derivative of a simple sine wave. Say sine Wt plus Phi and see what you get. Interesting, huh? So there's his formulas. And that's from the physics forums. Okay, so we're going to go on to the next video.